Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver, and today we're going to be talking about a little bit more tension. Now, we just finished a video talking about these two pulley problems. Be sure you go and watch it. We're now going to focus on this one. I just left them up to kind of just remind ourselves of some things we said over here, right? Because things can get a little confusing, all right? So this question is just about a person. They're on a tightrope. They're standing right in the center of the tightrope. Okay, and they just want to know, they're asking for the tension in the tightrope. What is the tension, right? And so they told us the length of the cable, they told us how far it sags down from its original height, which is about 12 meters, and then they tell us the weight of the person standing there. So the first thing that we need to do, right, and to find that tension is we kind of need to know that angle there, because we can see the tension, right? This tension vector, when we kind of look at this little free body, now we're going to draw a better one. When we look at this simple free body diagram, we can see that tension sits at an angle. And what do we know about vectors that sit at an angle? We need to break them into components, right? So we can't just do it. We weren't given theta. So we got to get theta first, right? We can see that once we get theta, we can break tension into components and see how those components, right, are kind of working out in terms of the weight of the person, right? How do they kind of come together in terms of the weight of the person? So, remember, in order to do that, we need that angle first. So how do we find that angle? Well, we were given some lengths, right? We were told that the length, the full length of the rope is 6 meters, right? Which means that each side, if the person, sorry, I had a kind of brain fart there. The person standing in the middle, that each side is then 3 meters, right? If this is 6 meters. And then they tell us that it drops down about 0.12, right, of 1.2 meters. It drops, once the person stands on it, it dips about 1.2 meters right there in the center where the person's standing. So those are actually kind of sides to a right triangle, right? This is kind of the, in terms of that angle, right, this is the adjacent side and this is the, right, opposite side, right? So we can use that idea to solve for that angle, which is really, really nice, right? So we got opposite and adjacent, which is what? Tangent, right? Tangent is opposite over adjacent, right? And the opposite here is 12 meters in terms of the angle, and the adjacent is 3 meters. So we solve for theta first, and we get it, right? We see that it's tangent, right? Or we do tangent theta over 0.12 over 0.12 meters over 3 meters, and then we do the inverse of tangent to get theta. So we have theta now. So now we have theta. We can now look at the components of tension, right? So we want to draw a new free body diagram. So in this new free body diagram, right, we draw the actual rope, right, which is the tension there, right? But we also want to think to ourselves before we start writing, is that the same tension? Yeah, I wrote it here, but is that the same tension? Well, yeah, it goes back to what we were saying over here, right? It's the same system. It's the same rope, right? Remember, T3, right, is the same all through here because it's the same rope. T1 is the same here because it's the same rope. So whatever's going on over here is going on over here. It's the same rope, right? They're just standing on it. So yes, the tension over here is equal to the tension over here. There's not something different going on over here versus over here. All right, so we can call those both T1, pointing in opposite directions, but that's T1 and that's T1. Whatever that's equal to, that's going to be equal to. Alrighty, and that's what we're looking for is tension, not just, you know, both those, but what, right? We're just looking for T1 is what we're looking for, okay? That's an important thing to focus on. So we can find it by using that idea if we know that theta. So we redraw our free body diagram using just these vectors as the tension, right? This right here, I drew them a little more pronounced here, but that's what those are. So this rope right here is going to give us tension, right? Both those are T1, like the blue right there, right, is T1. And then we want to break those two vectors, those two tension vectors, into their components, right? So for this tension, right, I know that the X, right, is going to be pointing this way, and I know for this tension over here, the X is going to be pointing that way. And in terms of the angle, both of those tensions will be equal but opposite, right? This is going to be, if this is negative X and that's positive X, T1X over here is going to be negative T1 cosine theta, and this T1X over here is going to be T1 cosine theta, a positive one, right? Now keep in mind, since this person is standing right in the center, These are separate, okay? There's kind of like a line right there with that person standing that's saying that there's a component of tension pointing that way and a component of tension pointing that way. Both of them are the x component of the tension right here, right? They're opposite of each other. And then the next tension that we have is right down the center, right? The y component. This vector has both x and y components, right? So in terms of that angle, we draw it right there, right? We always want to kind of enclose our angle. And so for this tension over here, you see that's T1y right there. And then for this tension over here, we see that's T1 right there. They're both positive, they're both pointing up, right? And in terms of their values, we see that since they're both positive, there's not going to be any negative signs, and they're both going to be opposite of the angle that they're related to, so they're both going to have signs. So this is T1 sine theta, and this is T1 sine theta. Again, both pointing up, so they're both going to be positive. Where this one, right, this tension in the x is pointing that way, this tension in the x pointing that way, they're opposite, right? So this one's going to have a negative sign versus this one's going to be positive. But these are going to both point up, both positive, right? This is important when we go to write our Newton law equation, right? So the other thing to keep in mind is when we go to put these forces together now, right, we want to think about what Newton law to use, right? Well, this thing isn't moving. They didn't say the person's jumping or anything like that. They're just standing there in the center. So if they're just standing there in the center, we're in equilibrium, both in the x and the y. So we can represent both x and y that way. Now I kind of wrote them a little separate because there's a little bit of different things going on with them, but you should be able to see what's happening here. So for the x, right, we write Newton's first law, then we want to fill in this side, right, from our free body diagram. So I always start with my positive, T1 cosine theta, right? That's my first x component of tension. And then my second x component of tension is negative, right, because it's pointing that way, T1 cosine theta. Again, they're both the same value because this is both the same tension. This is T1, this is T1. So they're equal and opposite, so when we combine those, they'll be equal to 0, right? And so they cancel themselves out. There's nothing to see there, right? In terms of the tension, remember we're looking at tension, and these are both tension. They're essentially like balancing each other, not canceling themselves out. We got to be very careful about what we say. But the y is a little bit different, right? So again, it's still in equilibrium, but when we look at the forces in the y, right, we have T1y from this side of the tension. We have T1y from this side of the tension. So both of those are positive, but we got to represent both of them in our equation. So there's T1y for this tension. There's T1y for this tension, right? And then minus mg, because mg is opposite of them, right? They're both pointing up, mg's down. It's kind of the same situation where? Right here, for pulley L that we had here, right? It's the same situation, all right? So, once we have that done, we want to fill in our free body diagram, fill in our equation from our free body diagram, knowing we're using Newton's first law. So, that's what we were doing, right? And so minus mg, sorry about that, there's the two T1y's and then minus mg. And then what did we say over here? Now, we normally don't do this step, but I know this is a little complicated, so I did it for you, right? This little step right here is then we brought these together, right? So T1y plus T1y equals 2T1y, right? And then that mg stays there, so minus mg. Now, you might say, well, Carl, that's equal to 0, this is equal to 0. I thought we're done. No, we're looking for tension. These are both tensions, so the tension in the x direction equals 0. But the tension in the y direction does not equal to 0, right? When we go to solve for it, right, we can clearly see that mg is going to have to come over, and 2T1 is equal to mg, and then we go a little further, right? So we can see that when we're looking for tension, because that's what we're asked for, in the x direction, the tension's equal and opposite, so there is no net tension in the x, but there will be some in the y because of the weight, right? And we can see that from this equation. So when we go to solve for tension, which is what we're looking for, right, we want to first fill in what T1y is, and T1y is T sine theta. Remember, we combine both T1y's, right? So now they're just 2T1y, or what we say 2T1 sine theta, because they're both T1 sine theta, right? And then the mg stays there, so minus mg equals 0. And then now we just solve for T1, right? Where 2 sine theta is going to come down. Well, first we bring mg over, right? And then 2 times sine theta is going to come underneath, which is what we have here. And mg is going to add over, and then 2 sine theta is going to divide underneath mg. right? Leaving just T1 on this side, right? And there's the tension, and that's how you get it, okay? So that T1 is the tension, right? We said that's a tension that way, that's a tension, that's the tension, right? That's the tension in the rope right there, right? It's equal on both sides, all right? So I hope that was helpful. If you have any questions, make sure that you're seeing your tutor, make sure you're going to SI, make sure you're seeing your professor and asking questions. Again, go back and watch these previous videos that we made prior to this, but they are related, and we'll see you on the next one.